So hello, welcome to another Physics 2 lecture. Today we're going to start chapter 24. Um, yeah, so the next few chapters are going to be us branching away from electricity and magnetism into some other topics, and it kind of has a good natural progression, to be honest. But this chapter really is the natural progression of what we were just talking about. Because what we did is we talked about electricity for a bit, and then we talked about magnetism last chapter. And this chapter is going to be talking about really how the two relate together. Before we get into it, I should talk about the elephant in the room, which is Friday's exam. So, yeah, Friday's exam. It went bad. It went really bad. Worse than I expected. It seemed from what I had looked at, most everyone apparently ran out of time. I did my whole I do it in 1/10 the time thing. I didn't think it was that much longer, but apparently it was. With how bad it went, and I mean, the average was a 51.5 with the max of 75. As I said in email, I curved the exam. This is my first time ever just curving a exam and not the class. But so many people didn't even get to finish the last problem that I decided it was safe. I mean, this was the breakdown without the curve, and it was just too depressing. So I did that curve where I multiplied everyone's grade by 1.2, which made this the breakdown. Um, with that, interesting. Sorry, an alert just popped up on my computer, but I don't think it matters what we're doing, so I'm gonna close it. With that, this is the grades in the class. Average in the class is 76. I'm not too upset about that. And makes this the letter grades in the class. Sadly, no one has an A right now, and a bunch of people have Ds. Almost a quarter of the class has Ds. But that is where we're at. I looked, a lot of those people with Ds, they also have low homework and homework scores and lab scores. Some, it was just the exam did poorly, but that's the setup. If you're on the low end of the spectrum, everyone is still well within able to keep their grade back up. I mean, the lowest grade was the only F was between 55 and 59.99. Everyone definitely has the ability. There's only 13 students who took the exam, I guess. 6, 12, 13. Yeah. Yep. Only 13 students took the exam. I think there's only 14 people in the class. One person didn't take the exam and he dropped it since then. So, yep. That's it for the entire class. So this only has 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nope, 13. Yep, there's only 13 students. But that's the breakdown for that exam. Any questions on that before I continue?
Is there any way for the next exam that you could upload like you did last semester with a PDF and we could print it off? Because I found me having to redraw a lot of things wasted a lot of my time.
The reason I didn't do that is because I had a problem last semester of people very obviously just copying and working on the exams together. And so the way it's doing this semester, it's randomizing numbers. And that's why I want to do it this way, is to lessen cheating. Because it was a real problem last semester.
Gotcha.
I had a bunch of people hand in 100% identical work. And it was a hard thing to deal with. This lets me, randomize bits. I will say, I don't think you're going to have to worry about drawing the pictures as much for some of the ones coming up. Though one problem you will in the next exam. But I'll try to make that less of an issue. What I might do, maybe, I got a plan on this. Maybe I will upload a second PDF with just the pictures. So no numbers on it. So that way, if you want it, you could download it. Would that work?
That might work, yeah.
Okay. I can have that because I did make it I did still make a PDF, but just had one set of numbers, so it wasn't visible. So maybe I'll have a second PDF. I'll have the exam, and the next year I'll just have a PDF of just the photos. So if you want to use it, you can. but it won't have any numbers written in it because, as I said, they're randomized. Any other questions? Okay, so let's get into it. So last chapter, we said, oops, that's not what I was trying to do. I was trying to do this. Last chapter, we said that if you have a moving charge, you can make a magnetic field. That's what current was, right? That a current is moving charges, and a current causes a magnetic field. Either, if it's a long straight wire, that mu naught I over 2 pi r equation. If it's a solenoid, the mu naught ni equation, which almost no one used on the exam, the equation for a solenoid. But here's the thing. Current can cause a change in charge, aka current, can cause a magnetic field. But it actually works the other way. With how well these are tied in, right? That we already know that like spinning a loop of wire in a magnetic field can create a current, but creating a current can. We already talked about that with the. No, we didn't. We talked the other way. We talked about Omoto. We haven't talked about that yet. Sorry, I'm getting ahead of myself. I'm just gonna say it with no proof. It just works the other way also. That a moving charge can cause a magnetic field, but a moving magnetic field can create a charge. This picture, which was the first slide, is a bunch of fluorescent bulbs that people just shoved into the ground without plugging in anything, just shoved into the ground underneath power lines. And the power lines have an AC current, which means the current is going back and forth real quickly. Because there's a moving current in that, that means a changing magnetic field. And the changing magnetic field lit up the bulbs. And this is the thing. Anytime you start changing the magnetic field, you can create a current. This is commonly called induced EMF. Now, EMF we talked about 2 chapters ago, the electromotive force, which is just a different way to talk about voltage. Normally, it's voltage is what you have over resistor. The EMF is what's supplied by the battery. Functionally, EMF and voltage are the same thing. I use them pretty interchangeably. They're in volts. They solve the same idea. It's just the EMF is supplied by a battery. The voltage is what everything else has. But we say that if you have a changing magnetic field, you can induce a voltage. You can make a voltage happen. And if you make a voltage happen, well, that's going to cause a current. Now, this was first discovered by Michael Faraday in 1831. In fact, some of the quantized pieces of this, which we'll see in a tiny, tiny bit, is called Faraday's law because he found it. What he did was he hooked a battery and had it looped around an iron ring, as you can see in this upper right picture. And then he put on the other side of iron ring another loop hooked up to an ammeter. And he saw that when he turned on the battery, there was a split second of current going through his ammeter, but only for a second. And when he kept it on, it didn't stay. Then when he unhooked the battery, there was a second of current. And what he realized, this came into play when the current changed. That it was when the current in the current going through the battery. Let me get my pen so I can draw. When the current in this loop changed, why was changing, it caused a current in that loop. And so he started figuring out how they were related. And what he realized is how they were related was due to the magnetic field. Is that it wasn't the current in that loop changing. It was that when that current in the loop, when the current was in the loop, it created a magnetic field. When that magnetic field changed, that caused the other current. In fact, I can show it to you. What I have here, this orange thing, is a big coil of wire that's hooked up, and I have it hooked up to measure voltage right now. So I'm actually doing straight induced EMF. And this white thing on the right side is just a magnet. And if you watch, when I bring the magnet in, there was a voltage. When I pull the magnet out, there was a voltage. If I just hold it in place, nothing happens. It's only while I'm moving it do you see a voltage. Make sense? You can also do the same thing with an electromagnet. This is just an electromagnet, but the same idea. That when it's stationary, there is nothing. But as I move it, I get a voltage. And you can see it's sometimes negative. And when I pull it out, it was positive again. It switches directions. And that's kind of how it works. When a magnet is moved towards a loop of wire, you will get a current or voltage. You can hook it up to measure either one. When it's stationary, there is nothing. But when you pull it away, it'll be a current again. And it'll be in different directions. That, going back to this guy, that when I pushed it in, it was negative. When I pulled it out, it was positive. And in fact, with my battery, or my magnet, this one was pushing in, it was positive. Put it out was negative. But if you watch on the video, I think I do it one more time like this, and positive, negative. Then I take this thing and I flip it around, and now it will go the other way, negative, positive. And so how the magnetic field changes seems to control how we create this voltage or current. Once again, you could talk about either one because we're talking about a loop of wire. But that's the idea. A moving magnetic field will induce current, which we can use to control various things. This is actually how cruise control in a car works. It's also how anti-lock brakes work. It's just moving magnets. Now, to quantize this, how we measure it, is we're going to talk about misspoke. We're going to talk about magnetic flux. And to talk about flux, I'm going to use this model I have right here. And I'm going to go to the dot cam in a second. This is just a series of spikes hooked up to a thing, right? Let's say you have I don't know what that A is supposed to be. That A shouldn't be. Oh, I know what that A is. Let's say you have a magnetic field that's constant, like this. Or my picture, right? That's just constant magnetic field going up. If we want to talk about induced EMF, we need to talk about the flux. Flux, which uses this symbol right here, a capital psi, and it's going to be psi sub b because it's the flux in a magnetic field. We can talk about the flux, the amount of magnetic field that goes through it. Quick thing, I'm going to give equations for all this in a second, but I just want to say a few things. The units of that are Webers. Also, you might notice that my Greek symbol isn't italicized. For some reason, I always italicize all my symbols. For some reason, uppercase Greek letters don't get italicized when they're variables. I don't know why. But here's the thing. When I talk about the flux, what I'm talking about is how many magnetic field lines go through an area. That flux is just the amount of magnetic field in a given area. So let's say this is my area, this square, right? What I would say is if I wanted to measure the flux, it would literally just be how much magnetic field passes through that spot. That this would be a pretty large flux. This guy would be much less of a flux, and so on. Now, if I say this is my area, how much flux passes through it is simply going to be how much magnetic field there is times the area. Because if I made this loop smaller, which I can't really do, but I'll just do this again, right? If I make it smaller, less magnetic field goes through it, I'm going to have less flux. When I keep it bigger, we have more. But it also matters the direction. If I go and angle this, like so, when I bring this down angled, you can see I only get 2 of these rows in it. That I have less flux because my area is turned. And that's how we're going to measure flux. That assuming the angle of our loop is perpendicular to the loop, aka we're measuring from the normal. That if I had to give a vector to this loop, I would say it's coming straight out of it. I'll say that the magnitude of flux is the magnetic field times the area times the cosine of the angle, where the angle in question is the angle between our loop and our magnetic field. And you can see, like, as I take this loop and put it at an angle, like if I put this at 90 degrees, I have no flux through the loop. And this will be used to define the flux through a loop. I didn't actually say that explicitly. But if you take a loop of wire, or just an imaginary loop, you can say exactly how much flux is going through it. Just how much magnetic field goes through it, the area, and the angle. So whether it's like this with maximum, or like that with less. Does that make sense?
Yeah.
So, as I already said, you want the angle to be from the normal. So 90 degrees At 90 degrees, there's no flux given because because none of the magnetic field lines pass through the area. At 0 degrees, we have all the flux because it can all pass through. But any angle in between will have some amount of flux in between. It literally is how much magnetic field passes through a loop. Now, Faraday's law, and yeah, Faraday, we mentioned him at the beginning. He's the one who worked this all out. Faraday's law, what it states, is that if you change the flux through a loop of while, it creates an EMF, which is a fancy way to say voltage. And he quantized it. What he said is that for a single loop of while, that the EMF is the change in flux over change in time. Now, really, this should be a derivative, but we're doing calc-based. But the EMF, change in flux over change in time. But there was a few things different from that. The first off is he said that's for a loop of while. But if we go back to the video I was displaying, right, when I brought this magnet in and out, that if I want to figure out the magnetic flux through that coil, I'm not going one loop of while. It's hard to tell because, you know, it's only so high quality, but this is a large coil. You know, here, I know how to explain it. If I wanted to do the magnetic flux through my slinky, I mean, I can go and put this on and talk about how much magnetic field is in it, but it's going to work to each one of these rings entirely. And so when I do this equation, I need to multiply it by n, where n is the number of loops. That the EMF through a coil of while will be change in flux over change in time. But if you have a coil of while, like my solenoid here, then it's going to multiply up the flux. The more it turns, the more it has. There's also this negative sign. That it's not just the change n times the change of flux or change of time, but there's a negative there. What it is, and this is the most important part of Faraday's law, so important it actually gets its own name, and I'll come back to that, is that it opposes the change. Now, if you're just doing magnitudes, sometimes, you know, if I ask just the magnitude of the EMF, you can ignore the negative sign, because I ask for the magnitude of the EMF, we're not going to care if it's positive or negative. But this is what is called induction. Induction, or an induced EMF, is any time you create a current by changing the magnetic flux. And in my videos earlier, you know, this guy, I was saying I was changing the magnetic field. By bringing this in and out, I'm changing B. Because I change B, I change flux. But that's not the only way to induce an EMF. It's changing the flux, not changing the magnetic field. In fact, and I'll cover this later on, but I'm going to hint at it now, if instead of changing the magnetic field, I just start spinning this loop and pretend it was actually overlapping with these, there's only so much I can do. If I change this loop, I change the flux through the loop because I changed the angle. That will also create a current and would make a current go around my loop. Anytime you change the magnetic flux through a coil of while, the change in magnetic flux over time times the number of loops times the -1 is the induced EMF. Now, Faraday didn't necessarily initially have that negative sign. That negative sign is its own law. That negative sign is defined by something called Lenz's law. And literally, in that equation, that negative sign, its own law, kind of fancy. What that negative sign says is that the induced EMF opposes the change in flux. Whenever you induce an EMF, what you're really trying to do, this came out of Odo, so I'm just making it all show up. Whenever you induce an EMF, what it's trying to do is it's trying to stop the change. That if you change the magnetic field, it's going to create a current to counterbalance that. That is what the negative sign means. If you increase the flux, the EMF is going to the induced EMF is there to try to reduce the flux. If you reduce the flux, the induced EMF is going to try to increase the flux. And I'm going to do that in a lot more detail in like a slide. But for now, I'm just going to say that's its plan. Also, this really, if you watch my video, right, it's not just all or nothing, that as I push this guy in and out, the number just kind of changes and fluctuates up and down. Those equations were for average induced EMF. If you want instantaneous, you're going to need calculus. There's no way to do it without calculus. But I'm just going to state for now, we're not doing calculus, so we'll just use average. Okay. Let's talk about that Lenz's law bit, though, that whole negative sign, what it means. Let's say I have a single loop of wire, just to make it simple, as shown in the picture on the bottom left. And in my single loop of wire, I have a magnetic field that's going straight up. And that magnetic field is slowly being toned down. That the magnetic field is changing as a function as shown on the graph to the right. Okay? So I'm just saying we have magnetic flux through a loop, and they're parallel. So it's just going to be magnetic field times area. But my magnetic field is dropping. What the induced EMF, that negative side, what Lenz's law says, is that it wants to oppose the change. So when we look at this, if B is dropping, that means the flux is dropping. If the flux is dropping, the induced EMF will try to bring the magnetic field back up. It'll try to bring the flux back up. If B is decreasing, it'll try to make B greater. And so it'll try to create a magnetic field up. Because let's think about this. If we have a loop of wire, and if we induce a current in it, we'll then have a loop of wire with a current. If you have a loop of wire with a current, you make a magnetic field. And so if the flux goes down, it'll induce a EMF in that wire in such a way to create more magnetic field up. And that means, using the right-hand rule, the current will be in this direction. That the current would be, if you look from above, counterclockwise, because the current being counterclockwise would create a magnetic field upwards. And if you create a magnetic field up, you're undoing the fact that the magnetic field is disappearing. That the induced magnetic field will try to undo the change you made. Does that make sense? It's one of the weirder things.
How do you decrease a magnetic field like that? Is that like from pulling it out?
You could do it in a bunch of ways. You could do it with, I think, phrases I shouldn't use the way I was about to. You could do it from just pulling out, like this, that when I pushed this guy in, I created a magnetic field, or I increased the magnetic field. When I pulled it out, I decreased the magnetic field. But you could also do it, and I didn't do this with this video, but with this solenoid, if I just left this sitting here and didn't pull it out, this is creating a magnetic field by being an electromagnet, right? But we know that the magnetic field from electromagnet depends on current. So I could have induced an EMF just by playing with the amount of current I passed through that green electromagnet. And if I, toned it down the current or toned up the current, that would also work to induce it. So you could do it if you have so you could change the magnetic field if you have an electromagnet, a magnetic field made by wires. Does that make sense?
Yeah.
Okay. Or you could do it, if you want just changing the flux, you could do it by changing the angle also. If you change the angle, that also changes the flux, which I'll come back to. So yeah, in this one with the decreasing magnetic field, it's going to try to make a magnetic field in the same direction to try to help increase back. Now let's say instead I took a small magnetic field and increased it. If I start increasing the magnetic field, it's going to induce a magnetic field to decrease it back down. In this case, my induced magnetic field is going to be downwards because my magnetic field was up. Because it's like, wait, you're making this bigger? Fuck that noise. I'm staying small. Reduce. And so B net won't change as much. And that's the goal in Lenz's law / Faraday's law. The goal in Lenz's law and Faraday's law is if you are changing B, it's going to make it as hard as possible to do it. It's going to create a current. And creating a current means creating a magnetic field. And the creation of that current, therefore a magnetic field, will try to undo any change you made. Okay? Now, once again, it really is change in flux. And since it's change in flux, that means you can induce an EMF. This is a little off on line, so sorry. By changing any of the pieces of flux. By changing the magnetic field or changing the area. which is one of the harder ones to do. But I'll get into how you can change the area in a second. I think I have a demo on how to do it with the area. Or by changing the angle. And for each case, if you start changing one of those, you will create an EMF. You will create a current. So this is an idea for how to do one with changing magnetic field. What I'm doing is I have this wire with a current I on the left side, and then I put near it a loop of wire. And so this is just, pretend my pen is the wire. So I just have a pen and then a loop next to it. If this pen has a current, it's going to create a magnetic field around it. If I start fucking around with the current in that wire, that will start changing the magnetic field. By changing the magnetic field, I can put a current through this. What this can allow you to do is create electricity in a circuit without a power source. That this loop can just suddenly start getting current through it, just by changing the current in a wire next to it. And in fact, if you have two wires near each other, we already talked about if you have two wires next to each other, they can have force, either pull them apart or push them away, depending on the directions. But you can also start adding current and changing the current, assuming it's changing. Now, if the current in that long wire is constant, then there will be no induced EMF. It only happens when it's changing.
When you mean changing, do you mean like with AC current, like it's reversing direction, like going one way
AC
and
will
then the
do
other?
it. Either with AC, or when I talked about this magnetic field changing as a function of time, going back to if I take my power supply and just slowly start increasing it, right? If I have a constant like 9-volt power supply giving me a constant like 6 amps of current, then it won't happen. But if it's fluctuating from 6 to 5 to full, or AC and just going 6, -6, 6, -6, 6, -6, 6, -6, they will both do that. Especially since AC is not an on-off, it's a sine wave. We're going to talk about AC, I think, next chapter, and I'll explain more of that as we do that. You can also cause the flux by moving the magnet. So if you have a ball magnet, the magnetic field is going to be more spread out the further away you are from it. And so if you take a ball magnet and move it around, this goes back to these videos. If you move the ball magnet around, you're going to be changing the magnetic flux in your coil because the magnetic field is going to be different in different spots. And by moving this around, I can induce my EMF. Now, I have a really cool example of this, which is one I would normally do in person, but, you know, not going to happen for obvious reasons. But I do have the thing. What I have here is a copper pole, and that copper pole has no magnetic field. You can tell I touched the magnet or the paper clip, getting ahead of myself. I touched the paper clip, no magnetic field. I then have a magnet. Touch that to the paper clip, it's magnetic, right? If I take my copper pipe, which has a slit in it so you can see, and drop the magnet in, the magnet falls slowly until it goes at the end. It doesn't go like, you know, full speed, 9.8 meters per second squared falling, but it's a slow process going through it, that it takes its time. And it even seems like it goes a little slow and you can't see it, which it probably does. The reason why is that's the same idea. When the magnet drops through the conducting pipe, that means a changing flux. When it has a changing flux, that induces an EMF. And so my copper pipe, which I'm going to use the GIF film just so I don't cover as much of the screen, that copper pipe suddenly had a current in it. That I was touching it, yes, but it wasn't enough for me to feel. But that pipe got a current, and that current is going to try to undo what's happening. And so what's happened is that magnet that's falling, it's going to create a current in the pipe. A current in the pipe is going to create a magnetic field, and it's going to create a magnetic field opposing the movement. The reason that magnet fell, this would be the same idea if I just took two magnets, one on top of another, and the one doesn't want to fall on the one guy, right? Is that with the two magnetic fields pushing away from each other, causing an opposing force. And so my magnet falling through my pipe, you know what? Let's go. My magnet falling through my pipe, if I look at forces on it, it'll have the force due to gravity mg, but it's going to have a force pushing it up due to the change between the magnetic field it is in and the magnetic field it caused, because it's a magnet in a magnetic field. But it's only in a magnetic field because it moving created a current in this copper pipe, and the current creating in this copper pipe creates a magnetic field. Now, I'm going to be honest, this is some weird ass shit. I'm saying the process of a magnet moving creates a magnetic field to stop the magnet from moving. But that's what it is. That's how this works. Okay? Here's a more grand demo of it. Once again, would be done in person. It's called the flying ring demo. What it is I'm going to take a coil of wire being, I need to draw over this being my coil of wire, and I have, this is just a solid iron piece that's sticking through it. Because it's sticking through it, any magnetic field created in this coil of wire is going to pass through to my iron shaft. Okay? What I did though is I hooked this up right to the wall outlet. You can see it's plugged in right there. That means it's plugged into an AC power supply. An AC power supply means the current goes as a function of time, as shown on this graph on the bottom. But if the current is doing that as a function of time, it's a solenoid. It's an electromagnet. That means the magnetic field, since it's mu naught I over 2 pi r, well, that's just magnetic for a wire. I should have put the magnetic field of a solenoid there. I should change that. The magnetic field of a solenoid would change as a function of time, right? So what I'm going to do is I'm going to put just a random loop of metal over this. And it levitates. The reason it levitates until I turn it off is because while it's on, what I'm doing is I'm creating a magnetic field, but I have a changing magnetic field. The second I put that metal loop on, that metal loop is now a loop of wire with a changing magnetic field inside of it. Because it has a changing magnetic field inside of it, it's going to create a current in that loop. And fun fact, if I keep this thing going, that piece of metal gets super hot because so much current goes through it. And because it creates a current in that loop, the current in that loop is going to oppose the magnetic field that's changing. It's going to create alternate forces, keep it from going up. In fact, if I take that same setup and I just start it turned off and then flip it on, I can launch that ring. Because the second it turns on, it's going to suddenly create a magnetic field to oppose it. Okay? Here's another practical use. And this is actually a practical use that I can really explain. It's how an electric guitar works. An electric guitar, what it is when you look at the pickups, which this guitar has 3 sets of, right? What they are is that the string is magnetized a little bit, just at a portion. And what happens is when you pluck a string, you're basically moving a magnet back and forth. The pickup coils in a guitar are literally just that. They are coils with them, and as the string moves, it's going to start messing with the current through the pickup coil. As it messes through the pickup, I'll just put it all up. As it messes with the current through the pickup coil, that's going to create. As the string moves, it's going to mess with the magnetic field through the pickup coil. Since it messes with the magnetic field through the pickup coil, that means it's changing the flux through the pickup coil. And if we change the flux through the pickup coil, we create a current. That current can be interpreted by the amp for your guitar. That's what it is. Any questions so far? Before I give one more practical example?
No, I think I'm good.
All right. My last practical example before I do a sample problem is, I'm sure some of you at least aware what a GFI is. It's the outlets like the one in the picture in the bottom right. A GFI stands for ground fault interrupter. It's outlets used normally around bathrooms or like near sinks in general, like you have in the kitchen. The general idea is these are outlets that if there's a short, they turn off, which is a fancy way of saying electricity passed through something that isn't a wire. AKA electricity passed through you, it's going to kill you, the outlet turns itself off. How they work is this picture above it is a picture of a GFI. What happens is they put a metal loop around the wire that basically would be the equivalent of, if I look at my outlet here, it's in the wall, would be here, but just drawing a loop around these two prongs, just the inside the wall part of those two prongs. What happens is that there's current on the wire, current goes one way in one end of the wire and the other way on the other. That means initially, even if it's AC, even if it's AC and they're switching, they're always opposing each other and they always balance out. Which means since the wires are always going in and out, they always create a net magnetic field of 0 because at all times they balance. Make sense? What happens with the GFI is if it ever isn't the same, if ever the current in does not equal the current out, that means the current is going somewhere else. Once again, like if you're electrocuting yourself, that's bad. If the current is going somewhere else, it'll suddenly go from saying that there's no net magnetic field in this loop to some amount of magnetic field in that loop. However much depends on what you're doing. And the second it starts noticing it goes from 0 to something, well, if it goes from 0 to something, that's a changing magnetic field, it creates a current. And that it creates a new current that goes to a sensor, that the sensor is basically set up that if it ever feels current, it kills the whole circuit. And basically, if a current is ever felt in this little loop here, it breaks off everything and kills the circuit entirely, normally by flipping one of these switches in the front. And that's what it's doing. It's saying if ever the electricity into the wall does not equal the electricity out, the second that happens, it'll create a magnetic field. When it creates a magnetic field, it's going to create a current. And when that current is made, that current is hooked up to a circuit breaker whose sole job is to shut it all down. It's just the idea of induced currents. Okay? Okay, I'm going to do a problem or two. We'll see how many I get through today. Pretty straightforward example problems. In the first one, I'm really going to walk through it because I've yet to really put any math to this. So try to explain as I go. Let's say I have the following. Let's say I have a loop of wire. And my loop of wire, ignore this lighter orange piece across for the moment. But let's say I have a loop of wire that consists of, 3 regular pieces of wire, jink, 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 and a third piece. That this third piece can move. That basically instead of a traditional loop, I have a piece that can move up and down, right? And what I say is that piece that can move is being pulled to the right with a constant velocity v. And so initially it was right here at this lighter orange, and it's being pulled to the right to this darker orange. And this whole loop is in a magnetic field out of the page. Oh, sorry, into the page. My question is, what's the induced current? Make sense, the situation? So.
Yeah.
Oh, not moving. There we go. If I want to find the induced current, and I ask for induced current in magnitude and direction. So let's start with direction. And for direction, we're just going to think about it. See, if this is moving to the right, the area is increasing. But flux is BA cosine theta. If the area is increasing, that means the flux is increasing. If the flux is increasing, the induced EMF wants to decrease the flux. Now, the magnetic field is into the page. And so we want to decrease it. Therefore, I need to induce a magnetic field out of the page. And so I'll just right-hand rule and say I want the magnetic field out of the page. Well, right-hand rule says that means it must induce a current counterclockwise. And I can say that current will be counterclockwise. Before I put numbers to this, a fun fact here. When it induces an EMF, that's then going to become a current carrying wire in a magnetic field. And since that current carrying wire is counterclockwise, that's going to mean it's going to be up on the piece that moves. But if I use my ILB, oops, I don't think that picture should have gone away yet. Oh, I guess it should. If I do my ILB sine theta, that means that that if I pull this piece to the right, it's going to get a current going up. If it gets a current going up in a magnetic field, there's going to be a force on it to the left. Kind of a fun fact that if I pull this thing bigger, its induced magnetic field is going to create an induced in EMF, which is going to create an induced current to resist the change and try to keep me from making it bigger. It won't put it back forward because the second I stop pulling, it's going to stop happening. Because the second I stop pulling, I stop changing the flux. But the process of pulling it, it's going to resist. That railgun I talked about last chapter, this is the biggest issue with a railgun. Because this is what a railgun is, that piece moving across. But that piece moving across is going to induce a magnetic field. Oh, sorry, induce a current, and the induced current is going to try to undo everything you do. This is a fun aside.
So none of this can exist unless there's movement.
Something has to be changing, either physical movement, as in this case, or spinning, or by changing the magnetic field. Because you can change the magnetic field without physical movement, well, at least it'll be electrons moving still, because you can change the magnetic field by changing a current. So it's less visible movement.
So like if they were stationary, it would be like one would be alternate, like the current would be alternating.
If this was stationary and it wasn't moving, there would be no induced current in this loop.
Unless the currents were alternating.
Well, unless the magnetic field was, whatever created this magnetic field.
Was alternating.
Yeah, which would probably happen by messing around with the current. Like in my example here, that this magnetic field was changing because it was hooked up to an alternating current. So the magnetic field changed. The magnetic field change created, the changing magnetic field created a current in my loop. Let me go back to the other one because it's easier to pause on. So the changing current created a changing magnetic field. The changing magnetic field created a current in the loop. The current in the loop created a magnetic field, which opposed the old magnetic field. This shit's crazy, and I acknowledge it. Okay, let's go back to my problem, though. So let's find the magnitude. You see the induced EMF. Once again, I'm ignoring the negative sign. The negative sign only has to do with direction. And honestly, the easiest way to deal with the direction is to work it out like I just did before. By saying, or not, by saying, okay, the flux is increasing. The flux is increasing, the magnetic field must be in the opposite direction. And that's the way to do it. If your flux is increasing, the magnetic field is going to be in the same direction. Sorry, if your flux is increasing, the induced magnetic field is going to be in the opposite direction. If your flux is decreasing, the induced magnetic field is going to decreasing. It's going to be in the same direction because it wants to oppose the change. But I'm going to ignore the negative sign because I already worked out the direction. And say that the EMF is the number of turns times change in flux over change in time. Well, the flux is BA cosine theta. Now in this case, theta though is 0 degrees. And also this is one loop of while. It says I have a loop of while, so n is 1. So that means my induced EMF is change in BA, change in T. But my magnetic field wasn't changing. If my magnetic field isn't changing, I can pull that out of that idea. And my area, well, my area is going to be how high the thing is up times where it is in X, right? That my area is this, which I called X, times this, which we called L. So I can plug that in. But L isn't changing either. So that means it's just B times L times the change in distance over change in time. But change in distance over change in time, that's some physics 1 shit. That's velocity. So the induced EMF is the magnetic field times this length times the velocity I pulled that guy at. Now I asked for the current, but V equals IR works for EMF also. So the current is the induced EMF over the resistance. And this would be the current in the while. And we know it's going counterclockwise. Now this equation isn't one like you can always use. This is special for this problem. But that's how you have to solve these. Questions? I have time for this next one? Yeah, I have time for this next one. Here's an even crazier example. Let's say I have a region of magnetic field, and the magnetic field is cut off somehow magically, that there's no magnetic field above this point. And I'll move my camera so I'm not covering part of my figure. And I take a loop of while and I just drop it. And the loop of while falls. So a conducting rectangular loop of while of mass m, resistance R, and its dimensions are W by L, falls from rest into a magnetic field B, as shown in the figure. During the time interval before the top edge of the loop reaches the field, the loop hits terminal velocity. What is terminal velocity? Seems weird. So what I'm saying is, when this falls, it's going to fall downward at a rate of 9.8. But right here, as it passes this region, it's going to hit terminal velocity and have no acceleration until it hits this. And at this point, it's going to accelerate at 9.8 again. That's what I'm saying. So what's the velocity as it's going from not in the field to fully in the field, just that time between? If I look at this as it falls, what I'm going to do is, so things are showing up weird here, is I'm going to define, give me a second, this y is not in the right spot. Y. I don't know what that v is supposed to be either, but I'll come back to that. Is I'm going to define y, the height that's in the field, the distance from, just that's in the field, from this line to this line. That's what y is. If I do that, I can say the flux is BA cosine theta, though once again, the angle is 0 degrees. So the flux is not going to be B times L times W. It's only going to be the part inside. It's going to be B times W times Y, because that's the only part that's inside there. The induced EMF, it's a single tone, will be the same idea as before. And just like the last one, I can use the same logic. And just like the last one, I can say, okay, it has an EMF. If it has an EMF, I can find the current. Questions that Dale? Now, I created this current. If I created this current, that means I'm going to induce a magnetic field. Because induced, anytime you have a current carrying wire, you get a magnetic field. Now, I got to figure out what direction is to make any sense of that. And if I want to work out the direction, I'm going to say the induced field will oppose it. Now, the magnetic field is out of the page. The magnetic field is out of the page and getting bigger. So it's getting bigger, so we want to make it smaller again. That means I have to induce a magnetic field into the page to try to decrease the flux. And my right-hand rule says into the page is clockwise. Now, I said, what's its terminal velocity going to be? None of these have velocity showed up here, but I don't know necessarily what I is going to be. But here's the thing. If there's an induced magnetic field on this, if there's a induced current on this loop, it's now a current carrying wire that's perpendicular to the magnetic field. So it has a force ILB. And so the force acting on the wire will be I, which we solved for, LB. And factoring that through means it's LB squared WV over O. But if I look at the force on this wire, right-hand rule, top has no force on it. It has no force because it's not in the magnetic field. The right-hand rule, ILB is to the right. The left is to the right. And I can get its value. The right is to the left, and I can get its value. But they're exactly the same magnitude, just in opposite directions. So they're just going to cancel each other out. The one going the bottom piece, IB, has a force upwards. And the length of that wire is just W. And so I can plug in L for W for L. And that's the force acting on it. But if it's falling, we have gravity too. Gravity should be pulling this downwards. And so what I can say is when it hits terminal velocity is when it has no net force. When these two cancel each other out. And using my F equals ma, I'll say up minus down, setting them equal to each other. And I can set the two equal. And if I multiply both sides by all and divide both sides by b squared w squared, I can figure out how fast it's going to fall. And that it'll for a little while stop accelerating downwards. That when you first let go, if I let go of this loop, it would start accelerating, but as it enters the magnetic field, it would stop accelerating and then would start picking up again. The same idea as this guy. It would be the exact same idea. Any questions?
So you're saying momentarily before that top wire enters that magnetic field, there's a magnetic field created by the bottom wire that creates
there's a magnetic field created by the entire loop.
Right.
Because that entire loop gets a current.
Right.
But the magnetic field created by that loop
fights gravity.
It's less that the magnetic field created by the loop fights gravity as much as the current created in that loop fights gravity. Because the current carrying wire in the magnetic field has it.
And we're finding that moment where it is just not moving for a second. Or however long.
No, it is not accelerating for a second.
Not accelerating.
So it's moved at a constant velocity.
So when it passes into the field, it moves at a constant speed, but it's not the same speed every single time. It maintains the speed that it was going at when it initially went in. So if it was going in at 5 miles per hour, it will continue to go 5 miles per hour. If it went in when it was going 10 miles per hour, it'll continue to go 10 miles per hour.
Not necessarily. Only if the speed happens to exactly match the equation I put below.
Okay.
Because the induced magnetic field is based off that velocity, that if it was traveling at the exact speed using this mgr over b squared w squared, it's going at exact speed, then it will stop accelerating. But if it's going faster, it'll probably still accelerate downward. I gotta make sure I do the math right, but I could be wrong. But it'll probably still accelerate a little bit, but it won't be at 9.8. Or maybe it'll slow down a little bit, right? That if you have the speed right, and as I said, I'd have to mess with how this would work. But if you fluctuate the speed faster and slower, you might have some acceleration. The acceleration won't be 9.8. It might even be upwards acceleration. It might actually start slowing down. It will never go back up the top, but it might start slowing down. But it would only at that exact speed would have no velocity whatsoever. Or no acceleration whatsoever. Okay?
Okay.
Ooh, I went over today. I'm sorry. I will stop there. And yeah, this stuff is weird. Sorry.
And it only exists to oppose what we're changing.
Yes. It'll always exist to oppose what you're changing. We'll get some more practical uses of that fact in a little bit. All right. I'll pick up on Wednesday. You don't have any homework due this Wednesday because it was a new chapter. But yeah, there we go.
I still do on Thursday though, right?
Yes, you still have a lab. That lab is based off F equals QVB, so.
Okay.